Thursday, we started a new unit, and we took a look specifically on Thursday at the discovery of the electron. Do you remember, prior to 1897, we didn't know anything about subatomic particles. We knew that there were atoms, and we knew that the atoms were different, but we didn't know that there was anything different about the inside of the atoms, or even that the inside of the atoms could be broken down into smaller particles than the atoms themselves. So along comes J.J. Thompson in 1897, performs an experiment with a cathode ray tube. In essence, the same experiment that people had performed for decades. But he did a little bit more than other people had done in the decades that would preceded him. Here's what the cathode ray tube looks like. In essence, it consists of an evacuated glass tube with 2 electrodes inside. This electrode we would call the cathode, and it's going to be the negative terminal, the negative electrode. The positive terminal over here, the positive electrode, is going to be known as the anode. And prior to 1897, when Thompson did his experiment, lots of people saw the same thing that Thompson saw, and that was this mysterious greenish glowing something leaving the cathode, going towards the anode, and then skipping past the anode and then striking the screen. Nobody knew what these things were, this mysterious greenish glowing. So they called them cathode rays. Cathode rays leaving the cathode, going toward the anode. Some people suggested that maybe they're electromagnetic radiation. Some people even suggested that maybe they're charged particles. But nobody really had any deep knowledge and verified knowledge of what these things were. So now we enter Thompson. Thompson introduces a magnetic field down here. And as these cathode rays, as we knew them at the time, entered this magnetic field, they were going to bend in a particular direction. Charged particles experience a force in a magnetic field. In this case, it would be a downward force. Thumb, fingers, palm points downwards. So we're going to find that they end up, the path of them ends up curving downwards like this. This in itself was enough to tell Thompson that we had negatively charged particles, not subatomic particles, not parts of an atom, but enough to tell him that it's negatively charged particles. We knew about negative and positive charge for years before we discovered the electron. We just didn't know where it came from. We knew that negatively charged particles would be deflected in this direction in a magnetic field. So this wasn't the big accomplishment. Okay, he said and verified the fact that they're negatively charged particles, but again, this isn't the big takeaway from all this. Let's do a little bit of analysis though. Thompson would have said that because the charged particles are going in a circle, and that's caused by the magnetic force, we'll say centripetal force equals the magnetic force. We'll say mv squared over r equals qvb. These cancel, and I'm left with mv over r equals q times b. Thompson knows what the value of r is because he can measure it by where the cathode rays strike the screen. He knows what the value of B is, the magnetic field, Kalen, because he was the one that introduced the magnetic field. He can make it whatever he wants to make it. He doesn't know what the value of M is. He doesn't know what V is. He doesn't know what Q is. So he hasn't really accomplished very much so far. He said that they're negatively charged particles, and he's shown that by virtue of the fact that we have them deflected in a certain direction in the magnetic field, but nothing really else. So this is where his genius comes in right here. He introduces another section, another chamber of this cathode ray tube with another magnetic field. That magnetic field will cause these cathode rays to be deflected downwards. In other words, a magnetic force acting downwards. At the same time, he has 2 parallel plates, one positive and one's negative, which will cause an electric force upwards. These particles are moving at different speeds, and some of them are moving too fast, some of them are moving too slow, that one force will be bigger than the other. And if that's the case, these particles are deflected upwards or downwards, depending upon which force is bigger. But we don't care about those ones. We care about the ones that are going at just the right speed, just the perfect speed, so that FE will be equal to FM. For those ones, When the forces balance, they're going to travel straight through undeflected. They're not going to go up or down. And those are the ones that we care about because those are the ones that are entering this third section, the blue section, that I like to call the main chamber. If we extend this, say FQE is equal to QVB, cancel with the Q's, we can solve for the speed of these particles that are undeflected. Remember, some of them are faster, some of them are slower. We don't care about those ones. We care about the ones that are going this speed because those are the ones that are going straight through and entering this main chamber. Once we have this, though, we can plug it in here. Now we only have two unknowns. So what Thompson does now is rearranges this to solve for Q over M. M goes down, B goes down. When he does that, he finds the value to be 1.76 times 10 to the 11. What's special about that number? What's important about that number versus some other number that we could have gotten, Mac? It's really, really big, yes. It's so big, in fact, that it's bigger than any other charge to mass ratio ever measured. And if the charge to mass ratio is so big, then what does that tell us? If the charge to mass ratio is so big, then the mass has to be so small. If the charge to mass ratio is bigger than any other charge to mass ratio, then the mass is going to be smaller than the mass of anything else. Even smaller than an atom. If you've got a mass that's smaller than the lightest atom, then that mass must be the mass of something that's smaller than an atom, a subatomic particle. So now we have the fact that it's a negatively charged subatomic particle, an electron. That's the discovery of the electron. All right? Now, there is one more section here of the cathode ray tube that we sometimes have to deal with, and that you hypothetically may potentially have to deal with on a hypothetical quiz tomorrow. In that section, I sometimes call it the acceleration section over here. And in that section, we have charged particles. We now know them to be electrons, right? Electrons accelerating through a potential difference. What do we do when charged particles speed up or accelerate? This goes way back to Unit 2. The charged particle speeds up. We think of it as a car going down a hill. And what's the energy conversion taking place when a car goes down a hill? Potential to kinetic. So here we're going to say EI equals EF, but this time the potential isn't going to be mgh, it's going to be QVI, and the kinetic, when it reaches the anode, is going to be 1/2 mv squared. You can solve for a speed there in the acceleration chamber, but remember, it's not the speed that we usually want, because the reality is the particles could be going slower than that. Some of the particles may not be going that fast. Okay, this equation assumes the energy conversion is 100% efficient, which is not always the case. We don't want the maximum speed of the particles over here. We want the speed of the particles. This gives us a maximum speed. This gives us a speed of the particles. So this is better. Okay, this is why Thompson wouldn't want to have used this analysis, because it doesn't mean that the particles are actually going that fast, just that they could be going that fast. Right? You guys comfortable with all three sections, including the first section, which hypothetically may appear on a hypothetical quiz that you may see on some hypothetical day, like, I don't know, maybe tomorrow? Yep. There's not really official names for them other than the middle one. The middle one you'll see often in books and so on, called the velocity selection chamber. Otherwise, I've just kind of made up some names. I call the third one the main chamber, but remember, that's not really an official name for it. It's just what I call it. And then the first one, I call it the acceleration chamber. But again, that's not really an official name for it. The middle one is the only one that we really have an official name for, the velocity selection chamber. In the end, Okay, what's important is that you know what's going on in each section as opposed to a name for them. I've just put a name on each of them just so that when I'm talking about it, you guys know which one I'm referring to. All right, you guys had 3 questions for homework last night on page 758. I want to take a look at all or 1 or 2 or none of those questions right now. Any issues with any of those questions? You know what? Actually, I want to do number 3 for sure. Pretty sure that there's going to be a few people with questions on number 3. Any others? No, besides number 3? No? Okay, 3 it is. 3 says a carbon-12 ion has a charge-to-mass ratio of 8.04 times 10 to the 6. Firstly, this is not a cathode ray tube if it's a carbon-12 ion. Cathode ray tubes use electrons. Mass spectrometers work almost the same way as a cathode ray tube, but they use ions, like a carbon-12 ion. So you don't change what you're going to do if it's carbon-12, but understand that it's not truly a cathode ray tube, and you're not going to use data about the electron. You're going to use data about the carbon-12. Has a charge-to-mass ratio of 8.04. We're going to find the radius of the ion's path when it travels at this speed through a magnetic field. If we think of this as a cathode ray tube, even though it's not really, which section of the cathode ray tube would it be? We'll say which section of the mass spectrometer, because that's really what it is here. Would it be? Yep. It'd be the 3rd section, what I call the main chamber, right? Because we've got just a magnetic field and it's going in a circle. So let's say FC equals FM. Let's say MV squared over R equals QVB. V's cancel. We're left with MV over R equals Q times B. And we're solving for the value of R. R goes up, QB comes down, becomes MV over Q times B. Now, here's, I think, where some people had trouble. You were given the charge to mass ratio. You were given Q over M. I don't see Q over M in this equation anymore. I see M over Q. What could you do here? What could you do here to get M over Q, which is, of course, what you want to fill in there? Yeah, you could flip it over. You could take this value right here and take the inverse of it. X to the minus 1, flip it over, plug it in there, solve for R. Or you could do what I personally probably would have done in this question, and that is not rearrange it to solve for R, but rather I probably would have rearranged it to solve for Q over M. And then I can plug in the value of Q over M, can plug in the value of V, plug in the value of B, and solve for R. R goes up by multiplying, okay, and then the value of Q over M goes down by dividing. Does that make sense? What you want to do here is make sure, first of all, that you're doing Q over M, not M over Q. You want to make sure that you're in meters per second, not kilometers per second. Notice his value for the charge to mass ratio. This is a little aside here. What do you notice about that value? 8.04 times 10 to the 6. Is there anything special about it? Tom? It's 100,000 times smaller. It's 100,000 times smaller than the charge to mass ratio of the electron. It's a lot smaller, right? There's nothing special about it at all. And then it's way smaller than the biggest possible one. If the charge to mass ratio is way smaller, then the mass of it is going to be way bigger, which we would expect. Carbon-12 ion, of course, is going to have way more mass than an electron is. Okay? So you get a question on a test, you're solving for charge to mass ratio, it will not be bigger than the charge to mass ratio of an electron. It can't be. Yep. We do the math there. It works out to be 0.037 meters. We good there? Or do we need to go through the math there? Go through the math? Okay. So let's sub that in then. Q over M is 8.04 times 10 to the 6. V is 150,000 meters per second. It's not 150 divided by 3.6 because it's not kilometers per hour. B is 0.50. Solve for R. R goes up. Q over M goes down. And then that should give us, check that on your calculator, but that should give us 0.037 meters.